Toby, give me a cheese.
What?
Thank you. Did you like that catch?
That was a tough catch.
Yeah, hold on. Can I ask you again? They call me They call me Sean calls me.
Oh, what happened on Death Day?
You were fat.
Wait a minute. I have to
You were fat.
Death Day. Wait a minute. OpenAI launched like some automation.
I'm playing Pekka is not Pekka free spam.
Toby.
Oh,
No, but give me like a tough one. No, it's not tough. I want one that goes up.
Wait, do you have like a stamp?
Adrian defend. Adrian defend.
All my money is gone.
Adrian defend.
This shit was $7.
Adrian, bro. Is it tough?
Alex might
Is it
rage
tough?
your
Mirror
if
3M?
he knows he has 7 on the
What?
Alex
No,
might
look.
rage your room.
We're taking the towers. We're taking
I
it.
don't
No.
have anymore. It's all gone.
You bought a share?
Adrian defend. Adrian
Oh, you
defend.
bought a phone?
Yeah.
I thought
Wait,
you bought a
only one.
share of a phone. Hold on, let me see the phone.
Adrian, bro.
Well, when you see those expensive debt.
Wait, take the case off.
6-7 cycle. No, not the city cage.
On everything it is. Look. No, we actually have a super.
General?
I'll be out on 13. It's so expensive.
Is it wrap homework? Yeah, it's wrap homework.
Why did you pick such an expensive? This is not cheap number.
If it's morning, I'm going to eat it.
Adrian defend. Adrian defend. Adrian defend. Defend. Actually, you're so high.
Oh, Agent Kid. Oh, that's what it is.
Nah, that's an actual one now.
I'll play boss man.
Okay, fine. I'll say.
I'll have bought for a spiritual journey. They're gonna make that. Hey, stop trying to make it doesn't make you feel
Okay. Hi everyone, thank you so much for coming to the third Physics Club meeting. Today's topic is statics, and this is what we're going to do in this meeting. Mr. Barrows is making copies of the problem sets, and I hope he gets back before we do this problem. I just start with announcements and stuff now. Okay, so these are your Physics Club co-presidents who were elected to the first meeting: Adrian, Henry, Madeline. These are their policies. If you have any questions, please ask any of us. It could be about questions about physics, questions about the clubs. Always. Also, because last week we had a guest speaker, Dr. Randolph, who very kindly came to HP to talk to us about atomically precise manufacturing. We're making a thank you card for him. It's this one on Gracie's desk. So please write something nice for him before you leave. Okay, this time we're going to be doing a problem set. The past two meetings were mainly focused on demonstrating to create lots of interest in the physics club. We talked about why is the sky blue and atmospheric optics during the first meeting. And in the second meeting, we talked about nanometering and lithography. But this meeting will focus on problems. We'll be talking about Newton's laws. By the end, I promise that you'll be a better problem solver. Okay, if you didn't get a problem set, you can find it online in the Google Sheet. So you can pull up the Google Sheet if you didn't get one. Every problem in the problem set has a chili level indicating its spiciness.
Oh.
1 out of 4. The physics here should be mostly straightforward. 2 out of 4. The physics here might be a little bit tricky to think about. 3 out of 4 or 4 out of 4. The physics here is pretty hard. It's okay if you get lost here. Regardless of the chili level, please feel free to ask any co-presidents for help at any time. Okay, so for this problem section, we'll be doing the problems in groups. In each group, we'll do a work example together first, introduce the idea. And after that, you'll get to practice the idea by solving one required problem, which is 1 chili, and there's harder challenge problems in each section as well. These are between 2 to 4 chili. You'll have 4 minutes to try the problems on your own, and then 4 minutes to talk about them with other people. Okay, but before we start with that, I wanted to talk about some background information about statics first. Okay, so statics are setups in which every single object is motionless. If an object is motionless, then by Newton's second law, we know that the net force on it must be 0. So this is the key idea in statics problem. We just require that the net force on every object is equal to 0. I chose statics because while the background information is really easy to state, the problems themselves are really interesting, really deep. So that's why I thought it would be a good fit for our meeting. Now there's 3 types of forces that show up a lot. The first is the normal force. The normal force is exerted perpendicular to a surface. So when I'm standing on the ground, I'm stationary. So that means the force on me has to be balanced. There's a gravitational force pulling me into the earth, but there's also a normal force exerted by the ground, perpendicular to the ground, which is balancing the gravitational force, and that's why I'm stationary. Now the tension force. The tension force is a force which occurs in like ropes, strings, and sticks, etc. The tension force is what holds the rope together. So to demonstrate this, let's suppose that I had a rope that was somehow attached to the wall. And let's say that on the right end of the rope, someone's pulling the rope. They're exerting a force F on this side of the rope. To illustrate the tension force, let's consider a part of the rope. We know that this part of the rope is stationary. So there must be a force that balances the force that someone else is pulling it. There must be an equal force in this direction. So the tension force is what holds the rope together. And the tension force must balance that force for this part to be stationary. There is a tension force on every single slice of the rope. And if you're curious, what causes the tension force microscopically are the forces between individual atoms. But you don't need to know that at all. You just need to know that the tension force holds the rope together. Okay. Finally, we have the friction force. The friction force is exerted parallel to a surface. So the normal force is perpendicular to the surface, but the friction force is parallel to the surface. And there's 2 types of frictional forces. There's kinetic friction and static friction. Kinetic friction deals with when 2 objects are in motion relative to each other, while static friction deals with 2 objects that are stationary relative to each other. In our case, we only care about static friction because we're considering static setups here, where everything is motion. So from now on, I'll only talk about static friction. Static friction can be characterized by the coefficient of static friction, μs. There's some surfaces with a lot of friction, like sandpaper, and there's some surfaces with very little friction, such as ice. The higher the coefficient of static friction, the more the friction there is. So for some common surface pairs, such as wood and wood, Teflon, that coefficient of static friction is 0.5. For Teflon, it's much lower, it's like 0.04. For rubber concrete, it's very high, it's like 1.0. The static friction also comes with an equation. So we can write that the magnitude of the static friction force is less than or equal to μs, the coefficient of static friction, times the normal force. Note the inequality sign. This means that the static frictional force has a maximum value of mu s times n, but that doesn't mean that it's always equal to this. Before solving a problem, we can't say anything about how large the static friction force is, except that it's less than or equal to this maximum value. In fact, most of the time, it will not actually be equal to the maximum value. It'll be somewhat less than that. Also, I wanted to say that the coefficient of static friction is always greater than or equal to 0, and usually less than or equal to 1. So if a problem asks you to find the coefficient of static friction, and you get a negative answer, or you get an answer that's greater than 1, then chances are that you did the problem wrong. Okay, so to illustrate that the static friction force has a maximum value, suppose that you had a really, really heavy box, and suppose that it's at rest, and there's friction, coefficient of static friction mu s between the box and the surface. Now suppose that you apply a small force to the box, not enough to move the box. Like you apply a really small force and the box doesn't move. Why does it not move? Well, the forces on it have to be balanced for it to not move. So therefore, there must be a friction force in the opposite direction which counteracts it. And the maximum value of that friction force would be mu s times m times g. But that's clearly not what the friction force is equal to, because mu s times m times g is huge because this mass is really large. So if it had been equal to the maximum value, the blocks would have gone flying to the left as soon as you pushed it. But because it's not equal to the maximum value, it's actually less than that. That's why the blocks are stationary. Okay, that was all the background information. Now we can do the first problem. So this is an example. We will do this one together, and then you get to practice on your own. So in this example, we have a 200 Newton sign, which is suspended by two cables. I want to draw all the forces as arrows starting from the center of mass and pointing away from the center of mass. What is the angle here?
40 degrees.
What's the angle here?
55.
Let's call this tension T1 and let's call this tension T2. We know that the forces are balanced because it's a static situation. Also, I forgot to draw one force. What force did I forget to draw? Okay, let's call it W for the weight. We can write F equals ma for the vertical direction. W equals T1. What's the vertical component of T1?
Sine. Whoa.
T1 sine 40.
What's the vertical component of T2?
Sine 55.
Okay, so this was F equals ma for the vertical direction. What's F equals ma for the horizontal direction?
That but cosine.
Okay. And, like, can you tell me the equation?
T cosine 40 plus T2 sine. Or
Yeah, it's very
cosine
close,
55.
but like, they're in different directions, right? If we choose this to be the positive direction, one of them is in the positive, one of them is the negative direction. Okay, so now you have a system of two equations, right? You have two equations, and there's two unknowns. T1 is unknown and T2 is unknown. But since you have two equations, you're able to solve for T1 and T2.
Wait, why did you do cosine 50?
Because I have to look at the horizontal component of each of these arrows. So I
It'd
can
be
like
55.
T1
I mean, what do you mean it should be 55?
has we can break T1 into two components, a horizontal component and a vertical
Am I
component.
right?
The horizontal component is T1 sine 40. The vertical component is T1 sine 40. What?
It's supposed to be 50.
Okay. You can try those problems in force balancing part 1 now.
Yes.
Is this 78 kilograms? Which one?
Is it weight because it's too much? Is it energy because it's
Numbers, bro. 78. It's like 78-ish. I didn't do problem 1.
It should be about 70 something.
Yeah, 78.
No, it should be 65. How about 1.3?
Oh, my fault. 78 sine 55.
Ah, sure.
Yeah, sine 78.
I don't want to figure that one out.
What's your
Or you use kinematics here.
This is what we get in Cypher. This is the dumbass we get in Cypher.
Chill, chill.
They're using it, bro.
Who doesn't need to calculate using these problems? Who's smart enough to learn these problems?
Use your phone, bro. I got some.
Am I supposed to be walking around? Now you got it. That's not mine.
65. I might be him.
Took a while, but
Adrian, do you have batteries I can borrow? I can use.
what do you mean? For calculator batteries?
Yeah. Adrian, do you want to switch batteries?
No.
Calculator batteries?
No, I do not. No.
This is my calculator.
This is mine. That's your name on it, bro.
like how do you?
This kid.
Oh, so you just like.
You're an idiot, bro. You're actually good.
But I don't know what to do. The realization is that is it moving? What if I try to the way? Okay, so that means how do I spell this T1? Is there an 8 This is T1 and T2, right?
I'm not telling you this. You want to try to do what I'm trying to do?
I need a.
You got this right.
Actually, you're fine too. Why are we on?
And we give it that. Yo, look how good it goes. And you give it that T2
Trying to figure out how to make it from. So it's not going to make it from. But then.
Yeah?
This is ready to degrees.
What do you think? I think it's in radians.
Yeah, but
It's in degrees.
implementing like the terminal into another site is so annoying.
You
I just want to make. Okay, so like this at you don't need to. You actually need to.
Yeah, I think it's stuff
Okay, so I haven't had it, right? I just focused on myself a very long time ago.
Bro.
I've gotten that out of the
I just said it's up to 4 years.
So like, if I want to be able to do all this, going one by one is so like, I don't know why, but I have like no velocity if I go one by one.
Where did you get this?
I have to do one by one, that's just how it is.
Why can't you not just do like
My AI.
Thomas, where you go?
Could be a faster player.
They're like the ants.
No, I could make this plan and then go through my workflow, my coding workflow, and just code it.
What'd you get for the first question? What'd you get? 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 What'd you get?
I'm not doing the questions.
No, 1.2. Idiot. What did you get, Cameron? You're so.
And then doing one task there.
Just kidding. Just kidding. I love you, Cameron.
I went out of town, I was going to study on like the 5 hours. I started my mini before I started studying.
I'm not serious.
Bus ride, this all studying.
No, they
It
would.
was so annoying. And now I have to.
They would do it on Sunday.
Okay, man,
Oh my god, that's kind of sad.
No, this camera can see my entire like exchange with Adrian.
And it's like, how do I
Yeah,
log in?
it's interesting.
It's always when it's still in the terminal, then there's.
You want to use it?
So it's
Wait, you
It's just like
plug it in the
annoying if I. No, this is my actual app is scale sales. Oh yeah, do you want to read my language?
Yeah, that's what I thought. I restrained myself
So like now it's a
Oh,
bit.
By the way, I only had
Swim line.
These technically claimed it. What's the vertical and horizontally?
You get one?
Then you start clicking.
Yeah.
Like, there should be no vertical horizontal movement, there should be no vertical movement. So when it's that FX equal each other, does anyone use FY?
You know what I got? You know what I got? You know
You
what I
get
got?
T1 cosine 30 equal to T2 sine. Okay, bro, what did you get then?
You know what I got? You know what I got? You know what I got?
JS.
You know what I got?
Which one is it?
I used to get.
I don't want to.
I got TL equals 106.05. Is that right? Is that right?
I'm not gonna have a talk to you.
You're actually an idiot, bro. I thought you were at C. I thought you were in C, Adrian. You failed me.
Okay, that's not good.
Hey guys, we're going over solutions for these problems. So please listen to Madeline.
Oh, this is the actual site.
So looking at problem 1.2, if we draw all of the forces from the center mass in the box, you can see the tension in the left string goes up 30 degrees from the horizontal tension, the right string goes up 55 degrees. And then the gravity force, which is just the weight, goes down. And then we can write two equations again, like in the example. One with the horizontal forces and one with the vertical forces. And then the one with the horizontal forces, it would just be the forces going left in the left rope, and then the forces going right in the right rope. So the horizontal equation would be cosine 30 times tension in the left rope equals cosine 60 times tension in the right rope. And then if you write the second equation with the vertical forces, the forces going up is equal to the forces going down, which is just gravity. And then the forces going up is tension in the left string times sine of 30 plus tension in the right rope times sine of 65. And then if you use substitution, like use the first equation to isolate one of the variables, plug it into equation 2, and solve, you can get both
Woohoo.
This is the next 1.4.
So did you get that? Did you get that, Cameron?
What's the answer?
Also not no, 106.05.
217.
Oh wait, Toby, by the way, is your mom picking you up?
We can draw another horse diagram.
Guys.
I'm getting picked up, but I'm not going to my house.
So this is just a diagram with like the given information. There's like there's a 20 kilogram box, and then there's two ropes 60 degrees, and then we don't know what angle that is, and then the tension in the left one is 160. So if we draw a diagram with all the forces, we can see the left rope, the right rope, and then gravity. And then once again we write two equations, one with horizontal component and one with vertical component. And then this time we have it's a little trickier because we don't know theta, but you can still write the equation cosine of 60 times the tension in the left rope equals cosine theta times the tension in the right rope. So that would be the horizontal forces, and then the vertical forces would be once again gravity, the downwards equals the two upwards. So sine of 60 times tension left and sine of theta. And then now looking at these two equations, it's a little harder to solve, but there's a cool method. You don't have to solve for theta. You can just directly solve for what we want, which is tension 2. And then by isolating cosine theta in equation 1, so cosine theta equals this, and then isolating sine of theta in equation 2 is this. And then we can use the trig identity. Sine of theta squared plus cosine of theta squared equals 1 to just get this equation with only one variable. And then after solving, you can directly get tension 2. But you can also just find theta and then solve tension.
Wow.
Alright, next example. This time is not about tensions anymore. This time we have a crate. So first step is draw an image. Let's say that the crate has mass M. Tell me what forces are acting on the block.
Gravity and normal. Friction.
What direction does friction act in? Opposite of the pulling force, right? Okay, can someone tell me what the magnitude of the normal force is equal to? No, be careful, it's not equal to n, because we also have this pulling force upwards. Yes. So, what is the downwards force? mg. And what is the upwards force? What is it? No. Mg plus n plus we want the vertical component of F. Okay, so we wrote F equals ma for the vertical direction. Can we write it for the horizontal direction as well? Okay, what is it?
Friction is equal to half cosine theta. Oh my god, I'm so smart.
Okay, and we want to find what minimum magnitude, what is the smallest possible F for which the crate will slide to the right. So remember that the frictional force is less than or equal to the coefficient of static friction times the normal force. And so, like, if you don't apply a large enough F, then the crate's not going to slide to the right. The frictional force will be enough to resist the F. Also, they should say static friction is a type of. So F is less than or equal to mu times the normal force. And whenever you are able to just move the crate to the right, then that means that the frictional force was not enough to resist the pulling force. And if that's the case, then F actually equals mu n. So in this case, F equals the maximum, because we're interested in the case when it just barely starts to slide. So we can say that F is actually equal to mu times n in this case. And now we want to solve for F. So from this equation, we know that n equals negative F sine theta plus mg. Now if we plug it in here, we have that mu times now we know mu, we know F, we know we want to find F, but we know sine theta, we know mg, and we know cosine theta. So we can solve for F now. So like now you did all the physics, and now you just have to solve the system of equations. U is 0.35. Okay, it would be better to combine the F's on one side first. I'm just moving terms around. Here I moved all the F's to one side. So F equals mu mg over cosine theta plus mu sine theta. You plug this in your calculator. You can still do that.
You're literally standing in front of the camera, though. Example. 1.1. Yeah. Why would you do 1.1? He did it for you.
Okay. Now you are free to. Now you should try problem 2.2, I think, from the set practice.
Cameron, you already know how to do this?
No. You know who knows how to do this? This guy does.
This guy does, bro.
Wait, Henry, why do you think you know how to do this, bro?
Same idea. I barely understood that.
Did we?
Doing the E&M lecture.
Yeah, I was completely lost, bro.
Why are you doing
No.
You have no idea what's happening when you guys on it?
Wait, Henry.
Hey man, these are the answers. It's 132 and 172.
Or just have to like sit down.
132, 172. I kind of. Easy enough. Oh wait, I did it. First draw.
Yo, Adrian, why do you have a glove?
Okay.
Me and Cameron are over.
What's wrong with right here? Did you wear this all day?
Yeah.
That's Cap. Cameron was not wearing that last period. What's your last period?
No, I'm Colorado, and then before that, I had my show, but I just stole a pair of black gloves and just.
Cameron, what'd you get? What'd you get?
Kobe hasn't even written the. I can draw it yet.
Right? Copy? You can't just copy that equation or something.
Yeah, you could actually.
Then like, yeah, I was looking
And then we have
It rests on the floor, so you know static.
and but we know that.
You say like 6, 7 really.
6, 7.
But we know
Yeah. How did you get the pole with the force of the force of gravity?
I got it.
Well, it's not really good. Why like multiplying by mass? But the acceleration of gravity. Why are you multiplying by mass? I don't know what's just. Okay.
I didn't know, bro.
Bro, I'm not giving you more pizza.
Is that right?
Maybe I should like actually want to.
Maybe.
I just practice. I'm like random.
Let's say you have the first part of the you have a student that.
And if I go Prez, Prez, do you have the key?
For that, yeah, I do.
Prez, did I get this question right?
Let me check.
I just want to see if I got it right.
Did I get T2 as 1 to 3? For example, 1.
1.1, I don't have the key for 1. Oh, 1.1, I didn't have the key for that. I only have it for 2.
Is that correct?
Yeah, I have
know what
2.2.
to do?
All conceptual. First one should be 74, like 74.2. It's easy more 2? Or 3.2 should be 74.
Maybe just morph another chemistry.
But it's the same thing. It's the same equation. It's 4 U and MU, but this is motion. U is not data. Then if you plug it in, just get it. It's the same reasoning as.
It's
the tension force. Bro, he didn't teach us kinetic friction. And teach us kinetic.
You get like a
How long will it take?
Andrew said he's getting great things. Oh, yeah, tell us. Bro, Miss Comfort is actually teaching FN.
Do you like her? Wait, James, do you like Miss Comfort?
Bro, no, she just does music the whole time. But it's boring, and she's teaching it like straight from the textbook. Like, Alex told me that y'all didn't learn like twist boats and twist twist boats
Pretty sure it should be 74.2.
in stereo.
Let me do it
Yeah, I don't know
really
where
quick.
she's breaking it from, but it's like
Have you ever compared the test from last year?
it's really strange. It's not really
Andrew said he just studied as well.
Yeah, it is 74.2.
I think it's pretty difficult.
I did Tristan.
I don't remember. I never had she taught AP how the science club, like the UIL science club. When I never taught.
This guy got 7,000.
We're lost. I think it's best if I just watch it.
How about I ask
I'm just gonna watch.
Okay, Adrian, you can do this.
I know literally nothing.
You do 2.2.
Yeah,
I'm just doing it.
Okay.
Yeah, but you didn't round it.
Where's your dog?
Wait, Adrian's gonna explain 2.2. So please listen up.
Raven, where's your dog?
Dave's just on for safety.
Claire Lou. Well, Claire's cookies are still Are they actually?
Claire's cookies?
I'll just give it a $5. She kicked up by Claire. I was there when Ellen and Claire made the name. I was also there.
I was also
I may have one.
You were not there.
I was there, bro.
I should get like a.
Alright, so first, correct? For 2.2, it says a 25 kilogram crate is on the floor and it's being put at 35 degrees.
Can you speak slower? I can't understand you.
Camera.
Sorry.
So, first you gotta figure out what friction is. So, in this case, because you want it to move, you want to assume the maximum, so therefore, it would equal to U times the normal force. And the normal force in this case is equal to, its normal force goes upwards. So the upward forces here, there's a downward force of gravity, mass times gravity, and there's an upward force of this F sine 35. So normal force goes upwards, therefore it's the vertical forces adding together. So this becomes negative, so this becomes N is equal to F. That. Everyone got that? Shoot. Oh yeah, no, my bad. It is the opposite. Never mind. Okay, but this is what normal force is. So then what you get is F, this is equal to U, which is 0.3, mass is 25, 9.8, minus F. Actually, I'll do this. You get F is equal to simply, yeah, so you want the horizontal force, which is F cosine 35. Eventually, you want this equal to the friction force. Which is, okay, so, am I wrong?
No, you're good. Sorry.
Yeah. And this is in order to simplify, but it just becomes this. Then when you plug in numbers to this, U is 0.3, M is 25, G is 9.8, and you get F is equal to 74.2, which I don't feel like
I'll give you guys 4 more minutes and then we're going to move on to torque balance part 1. So try problem 2.3 in the last 4 minutes.
How do we do kinetic?
Here's a thing like this. Instead of running backwards. Adrian is so cool.
yeah, I think you can do that.
Yo, I forgot how to do kinetic friction. How do you do kinetic friction?
So it balances.
Why is there a force?
What is Orchis conduct?
And the F, right?
Documents.
Really not ready.
Okay, how hard is it? How hard would it bring the cookies up? Only first It cannot be that, bro.
Come on, bro.
Sean, you already know Sean is ready. You already know Sean is ready. You already know Sean is ready.
I can say F who's 135.
I know.
You have to get perfect score in the if you like that, I would keep going. I don't like SAT. This is not.
This equals This is like nonchalant. Henry's so big. I don't actually
Oh.
Luke, what's that? So,
Wait, Raymond. Remember when you were talking about like peace?
I like it too. I was too lazy to like
Oh yeah,
so much
another one got us 15, 20,
what I used to take out module 2 is always
What'd you get?
I don't like how the terminals are like.
Go read 5 seconds of equation.
I understand that.
What'd you get on this?
Remember in my diet?
And Ron got 1400.
What's going on with this thing, bro? Why is there particle? Why is there fluid?
I just didn't feel like confident. I was like, nah.
Bro, everybody already
Okay. Hope you guys had fun working on the force balance
There's
puzzle.
0% chance.
Now we're going to talk about torque balance. This is the prototypical guys. Torque balance is like the best way to think about it is you imagine a seesaw on the playground. Okay, so now let's consider this example. Let's consider by Newton's first law, Newton's second law, we know that this is motionless. So therefore, we need to know that the forces on it are balanced. So if we write F equals ma in the vertical direction, then we get that F1 plus F2 must equal F3, because otherwise it would have some acceleration vertically. But also, we know that F1 times A equals F2 times B. Oh, no, sorry. Okay, so there's two ways of writing torque balance. So whenever you write torque balance, you need to choose an origin. In this case, I'm going to choose the origin to be right here. And then the product, torque, is force times distance. So in this case, force times distance is F3A, and it's pointing in this direction. And then this one is F2 times A plus B, and it's pointing in the opposite direction. And if it does not rotate about this point, then we require that F3 times A equals F2 times A plus B. That's the statement of torque balance. And this is actually a very useful statement. And you can prove torque balance using Newton's laws, but we won't prove that right now. If I chose a different origin, such as this point, then I would have a different statement of torque balance. They're both valid. You can choose the origin to be whatever you want. You should choose it to be a convenient value. So in this case, we can write torque balance again. F2 times B is pointing in this direction. So like, if you imagine a clock, this is moving in the counterclockwise direction. And then this one is moving in the clockwise direction, right? It's moving in this direction, which is clockwise. It's moving in this direction, counterclockwise. So therefore, they have opposite signs. So F2B minus F2A, or minus F1A equals 0. Because there's 0 rotation. This entire thing is motionless. Now, in our case, we're working with statics. That means you can choose the origin to be wherever you want because the net force is 0. If you do dynamics, and then you'll see that when stuff is moving, then you're more restricted on what origin you can choose. But like, I'm going too in depth here. You just need to know that you can choose the origin to be whatever you want in the case of statics, and you should choose it to be a convenient value. Okay, you can try problem 3.1. 3.2, sorry. Will you sign this? Yeah. Will you sign it?
Nope.
What should be the ratio?
It's just that
Lily.
Or Adrian's way
Did you send me the
funny thing is, I don't even know. Thank you.
Henry, did you write this?
Thank you.
How did you try to believe it?
How in the world did I do here?
Okay. Did you write this?
Yeah.
Okay, that explains a lot.
Wow.
What does that mean?
Handwriting is beautiful. What is the distance?
Not rapid.
Oh my god.
In what direction the normal force is going? It has to point perpendicular.
2.2 is 0.3, 2.3 is 0.1, 5.
I want to show this as my work. So what's the distance between this line and
Yeah.
There's this tendon, which also.
They asked you for 1/4. They asked you to find. They asked you to find F1.
Oh, Max is here to sign. Max is the one that got a selfie with him. Did he have to get a selfie?
Yeah.
There's like zero.
I don't remember.
No, they're.
It's talking about like neurophysics. Or just like brain shift. They were talking about
What is?
I used to study
He was talking about like super microscopic lasers. He's talking about like chip compute or something. Something about compute.
F2 is the photograph. Which way would I do F2 is go outwards?
So it's be a bomb.
You have to do something with
Oh, bro. I asked don't kill yourself. You won't I asked Jason that question. He really said my dad. If I didn't find a job that I liked, I was going to stay unemployed.
You're given the map that you have to find. Now,
Be unemployed is cool.
That sounded awesome.
You could be a bum though. Or you could be an
You don't have to do
entrepreneur.
anything.
You know what they say? The S stands on the inventors.
Risk taker.
I'm a risk taker. I'm a road runner.
9.8.
So what's your profession?
I'm a risk taker, you know, I'm a road runner.
and then there's normal force and here.
So what
And
risk
then
taker
there's
is it?
force balance and here. So this distance, 20 times n has to equal this times this distance, which is 5.
I that's some tough
So can you write that as an equation?
Playing poker
This is
builds
the
your
horizontal force, right? Doing this one.
Is it actually?
Yeah,
But then like those are like.
It builds your seriousness.
No, it has.
And I know you need that.
I guess they
You need to stop.
Bro, you need it more than I do.
Also like this was
You're sitting in bed by $1 million.
Berserk.
You should have to memorize it.
Dude, I don't do anything. I don't know what. What'd you get on that?
Did you sign the poster?
I did.
Adrian's gonna be explaining 3.2
For what? For what?
You got a 9.
Which one?
100.
Oh wait, sorry.
Explaining.
She checked. I
Oh yeah, this is the.
He's explaining it.
So I
So
did
that's
Yeah.
Why is that? That's like.
You realize Adrian doesn't do anything, he GPTs everything, he's still
Like Cypher. This compared to Cypher just like the rest of the teacher, bro.
Dude, this compared to Cypher is actually trash.
This is actually like taking
It's just-
candy from a baby, bro. I mean, Cypher's not.
This Cypher, that's me. Most difficult.
Okay, so for 3.2, the Achilles problem is force based, but you want to take the origin at the toe. First, you want to consider the horizontal forces. The foot isn't moving up or down, right?
Yes.
This means that the horizontal forces must equal 0. So the forces here is the tension in the Achilles, which you're trying to find, obviously equals upwards. There's the force of gravity, force of weight going downwards, so it's force of gravity, I guess. Then at the toe, there's contact. Let's say, when there's contact here, there'll always be a normal force going this way. So this means that, what does this mean? This means that it doesn't matter which way you write it, but T plus N minus mg must equal to 0. And what? Okay, so m is equal to 60, g is equal to 10. This gets you 600. Oh, okay, then the torque on the toe isn't moving either. This means it's not rotating like this way. Either way, it's like that. It's staying. Basically, it just means it's staying still at a point. So, torque in this case is given by, I guess you could say it's equal to radius times force times cosine theta, or you could just say it's the horizontal length here. So this means there's 2 points, there's 2 separate ones, meaning the toe, the torque here and the torque here must cancel each other out in some way, shape, or form. I don't exactly remember this line. I think this was 20, and I think this was 25.
Yeah.
Okay, what else is it? Oh, I wrote this part slightly wrong. The normal force is equal to the weight. We do not know what this force is because there's stuff. Say this is.
Check calendar. Just shoot me now. All things you can make that.
Okay, so we could rephrase it like this. This is the force going contact from the fuzz to the ground. Normal force going upwards. Normal force will always equal I think the weight in this case, otherwise there would be balance. I'm pretty sure. So you get F is equal to N plus T, and this torque must equal to 0. Therefore, 0 must equal to well, it's equal to radius cross force. So the radius here is, what is the radius here? The radius here is 20. The force here is FL. Radius here will be 25, and the force is T. Because they go in opposite directions, one of them will be having a different sign. Just say that for now. So this was equal to this minus 20FL. And I think I solved it from here or something. This is equal to then normal force is equal to the weight, so it's equal to 600. And what else? Okay, well, I guess you could just substitute this in for 0, if that works. Okay, yeah, this works. Then you just, when you solve this, well, when you solve this, you just get T is equal to 2400. Because you get 1200 is equal to 5T, 1200 divided by 5 is 2400. That's
You can also do it in a different way. So Adrian showed us how you can take torques about this point, and that's good. And the method is correct. And you can also do it a different way. You can take torques about this point instead, which is what I showed Chrisia. So if you take torques around here, then you consider this force and this force. Like this one does not affect the torque about this point because its distance is 0. That's the advantage of taking it here. So like if you didn't know this force, then you would have to take it here so that you can write the torque equation without knowing this force. But if you like don't know this force, then you could take torques around here, and then you only need to know these two forces. Okay, the next question is very nice. So next question, 4.1. So in this problem, you're told that there's a ladder which is resting against the wall. So there's two there's two surfaces here, right? There's the ground and then there's the wall. You're told that the coefficient of friction between the ground and the ladder is mu. And you're also told that the coefficient of friction between the ladder and the wall is 0. So this is a frictionless surface. This surface has friction. And you need to find the normal force N, which points perpendicular to the wall. That's what you need to find. So first of all, we don't need to use torques yet. Let's first write the F equals ma equation. So in this case, we can write that because the ladder is stationary, N must equal F. These are the forces in the horizontal direction. And we can also write it in the, there's also a normal force here. To balance that, because gravity down, we need to balance that force. But I think that we don't need to consider this force. I will only write the F equals ma in the horizontal direction. Now we will write F equals ma in, now we will write the torque equations. Can someone tell me what this distance is from this point to this point? I want to consider torques about this point. So what is the horizontal distance between this line and this point? And remember this angle is theta. So if you can draw a triangle. And there's someone else who's theta. And I want to know what is this. What? I didn't hear it. Well, I just want the distance, not like the component of it. And remember the length of the ladder is L? Oh, I didn't say it. Okay. The length of the ladder is L. So, okay. If we say that the length of the ladder is L, then this is L over 2, right? This top part, and this bottom part is also L over 2. So then this part, like, because sine theta equals opposite over hypotenuse, this one is equal to sine theta times L over 2. It's this one. So these are pointing in opposite directions. This one's pointing in the counterclockwise direction, right? If you take this, like this is in the counterclockwise direction. And then the normal force is pointing in the clockwise direction about this point. So they have opposite sides. So sine theta times L over 2, this is the distance, and then you multiply by the force, which is mlg. And then minus, because this has opposite sign, of n times the distance between this point and this line, which is L cosine theta, equals 0, because the net torque equals 0. And now we can cancel L. And we're also given that n equals F. And we're given that the ladder is on the verge of sliding. So if it's on the verge of sliding, then F equals the maximum, the frictional force equals the maximum possible value because it's on the verge of sliding. So we can say that F equals mu times the normal force here. Okay, but the normal force here has to equal mlg because it's not moving in the horizontal direction. So this has to be balanced by that. So F equals mu times the normal force, and the normal force equals mlg. So mu times mlg. And I realize I'm being confusing here. Let's say n prime, because this is n, and this is a different normal force. This is F, and we can plug it into this equation, because F equals n. We can cancel G. We can cancel ML. And now we have that sine theta over 2 equals mu cosine theta. Wait. No, I did something wrong. Okay, I don't know where I made a mistake, but how about we let Henry explain?
And then a frictional force, right? Does frictional force matter?
Yeah.
It's like this, right? Whatever, doesn't matter. Okay, so we take the, what are we talking about? Force, yeah. So we know that the length is out. We know that the angle is what, 35 degrees? Is it
Theta.
Wait, this angle is theta.
Yeah.
And this equals theta. Okay. So, since the net torque is 0, say that MLG, I said create a variable for the base. The entire base is B. The horizontal distance would be B over 2 equals, and then the height is H. And times H, right? Then N equals MLG over 2 times B over H. And we know B over H is the tangent of theta, so MLG over 2 tan theta. There we go. Let's try that.
Yeah. Do you want to just explain the next one?
Sure.
I'll link through.
So now there's a person standing on a distance x above the ladder. His weight is MP. So now it's basically the same thing. We have MPG times, we want this distance. So I use similar triangles. X over L times B is going to be this over, like, no, plus MLG times B over 2. This whole thing is going to be equal to NH. Because these two are pointing in the same direction, and this one's pointing in the other direction. So, NH is equal to I think I said B over L is going to be sine of theta. I don't remember what I did.
Yeah, I think you did that.
Actually, I think I went from sine of theta to B over L. Oh, I see what I did. Okay, again, I just divide both sides by H.
Okay, this one we already did all the physics. We just have to find the end now.
And then again, B over H is going to be tangent of theta.
Don't forget the B. Oh, yeah.
And then we factor out a G and a tangent of theta.
problem is there's like a rope suspended between two trees. Oh, can you tell me what the problem is?
There's a uniform local weight W that answers the record at the same time. Communicate them into a row.
So you have to find.
Determine the tension of either end of the rope and the tension of the rope.
Okay. So first, let's do the part A. Is find the tension at the ends of the rope, right? So in this case, the tensions are not the same throughout the rope. At the ends.
The center of the rope is 0.
So we will do F equals ma. So first, let's take the system to be the entire rope. Now let's consider the forces that are acting on the system in the vertical direction. First of all, there's a weight force acting downwards. But the rope is not moving, so this has to be balanced by the tension force applied at the ends of the rope. The tension force points along the rope. This angle is theta. So what's the vertical component of the tension forces? The horizontal component of the tension forces balances the weight.
T cosine theta.
2t cosine theta, right? Because there's two of them. So T equals W over 2 cosine theta. That's the tension at the end of the rope. Okay, and then Henry asked, isn't the tension at the center of the rope 0? But you'll soon see why that's not possible. We just have to choose a different system. So in this case, I chose the system to make the entire rope. I'll choose a different system in this case. Like in this case, I just want to say one more thing. The system was the rope, and then there were external forces acting on the system. The external forces attached the system to the trees. In the second case, you have to find the tension at the center of the rope. In order to do that, let's choose our system to be half of the rope. What direction does the tension force at the middle point, by the way? Like, what direction does the tension force here point? Oh yeah, left or right, along the rope, right? And the rope is horizontal here, so the tension force points horizontally. Okay, so remember there's a tension force acting on this part of the system. Right? And then this half of the rope is stationary, so it has to be balanced by the tension force here. So T equals T sine theta, or let's call this T prime. T is the value which we found in part 1. T was equal to W over 2 cosine theta. So T prime equals W over 2 times tan theta. Okay. What's the next problem? Let's do this one.
It's 6 identical columns.
The one before that. The one before the one we just did. The rope hanging from the ceiling. Can you read me the problem?
When rope is on the cell and mass per unit length lambda means vertical point under tension as a function. Find the tension T of y as a function of height y or both of y.
Okay. But basically, you need to consider a point on the wire, and then you write F equals ma for this point. So let's say that this point is distance y above the bottom of the ladder, and the total length of the rope is L. So then the mass of this section is equal to lambda times y. And this mass of, okay, and then we just need to write F equals ma, because the weight of this section of the rope is lambda yg. And this rope would ordinarily fall because there's a weight force which is acting down on it. But the weight force is balanced by the tension in the wire, in the string. The tension holds the rope together. So this has to be equal to the tension force. So they wrote it as like T of y. So this is what T of y means. So in order to find this expression, we did force balance on a suffix of the string, on the bottom part of the string. Here, read the problem.
If identical blocks are not stand connected in a horizontal line by massless weighted rods placed on horizontal surface with their coefficient of connectivity. The leftmost block is pulled to the left by a horizontal force F causing all the blocks to slide to the left at a constant speed. Determine the tension of the rod on the third.
Okay. So here's one possible way to do this problem. It's a very bad way, but I'll tell you it. Let's make variables for every single tension. And then we can write 5F equals ma equation for every single, we can write 5F equals ma equation, or 6F equals ma equation for each of the 6 blocks.
That's a great idea.
And then if you solve those 6 equations, you'll be able to find F, T1, T2, T3, T4, T5. And you say F as your answer. Okay. The second way allows us to do it without bashing a bunch of equations. I want you to find the tension in the middle rod. I think that you take this as your system. It wants you to find tension here. Okay, so we're given that it moves to the left at a constant speed. That means that it's not accelerating at all. So that means that because A is constant, the velocity is constant, therefore A equals 0. So therefore there's no force on, the net force is 0. So what's balancing the force F? There are 2 things balancing it. First of all, there's the tension in this rod, T. Second of all, there's the frictional force acting on each of these blocks. So we can write the equation. So then you just get T instead.
Wait, but like you want to be able to do that if it wasn't asking for it. Wait, or just
You
take
can
a
do it
different
for any of
system.
them.
You would just like take a different.
Take a different system. Like if I wanted the 4th one, I take this system, and then I change this to a 4. So it's about the 2 miscellaneous problems are both about choosing a clever system. Yeah, I understand.
Wait, so you just say F equals the friction force plus the tension?
Yeah, because you have to balance in the horizontal direction. Wait, but I think you can make F equals MA way better than I was last time. I got really lucky last year.
I'm not making it. Did he get a medal sophomore year? He got like silver medal.
No, he got top 30. Gold medal.
What the heck? Wait, so he got top 30 gold medal and he got number 18. He got top 18 JMO. And he didn't qualify for AMO or what is this one? Yeah.
Wait, he didn't AMO? He said he did.
That's actually crazy.
Oh, same. Even after sophomore year.
Alright, Tristan, I gotta head out.
Okay.
Thank you. Actually, I have it locked in. I got 2.1 by myself, but I like plugged in 3 instead of 0.35.
I'll just do everything. Okay.
You got it?